Section 13 is about filtration. Based on drinking water standard in the US and most other countries, surface water should be filtered and disinfected. Desettling does not remove all flux, so you cannot remove all of the bacteria by killing microbes, Giardia for example, Legionella, and other bacteria. So you need to design filters. Settling does not remove all flux. Further treatment is required. Filtration provides the additional opportunity for separation of small flux or particles. This separation is introduction to filtration technology, concepts, and design. So here you see the overview of solid-liquid separation alternatives in water. For conventional system, what you have first water system, then you put water in coagulation and then flocculation units, and after that you put in filtration. And it can be after flocculation, if you have settling and then filtration, or if you have flotation plus filtration, we will call this one conventional treatment plant. But if you remove settling or filtration, it will be direct filtration. Types of filtration, it can be granular media filters, so slow sand filters, rapid sand filters. We have high rate granular media filters. These are common filters or conventional filters. Also for advanced treatment, we have membrane filters, microfiltration, ultrafiltration, nanofiltration, and another filtration is cage filtration. So when you have filter, we have to see what happens to the particles inside the filter. As you see here at horizontal axis, you have particle sizes in microns. And here, for example, you have viruses. The size of viruses are from 0.01 to 1 microns. And the technology that you need to use is membrane filters. For bacteria, as you see, starts from 0.1 to, let's say, above 30 or 40 microns. And you can use membrane filters to remove bacteria. So for suspended solids, if you remember, we practiced in class, starts from 1 to 100 microns. And here are, as you see here, the technology that you need to remove suspended solids. Let's classify the filters. The first is slow sand filter. So we have here, as you see, filter rate. I put here as meters per hour. So this is the velocity of the water in vertical dimension. So for filter rate for slow sand is 0.04 to 0.4 meters per hour. And for rapid sand is from 5 to 10, but in US units it will be 2 to 4 GPM per feet squared. GPM stands for gallons per minute, so gallons per minute per square feet. So for high rate, it is 1 to 2 gallons per minute per square feet. And at the right, you see the media size and the bed depths. So media size for slow sand is from 0.25 to 0.35 millimeters, and the bed depth is 1 meter. So here again, for rapid sand from 0.45 to 1 millimeters, and then the bed depth is 0.5 to 1 meters. So let's see what is the layout of sand filters. This is one, if you want to see the diagram, what is the diagrammatic layout of sand filters. Here is the one sample of the filters. At the bottom you have, we see here gravel, then the next layer is sand, and the other layer is anthracite coal. At the top you see troughs. So that is, we will talk later in this later. So we'll talk about the backwashing. Backwash means we have to backwash filters. Let's see what happens in the filter. If you see here at the left and the top and left, you see the inlet, water enters, and you filter water from the top to bottom, and then you collect treated water from the bottom of the tank. But after 24 hours, depends on the filter, it depends the quality of the water, you backwash it. And when you backwash it, you take water from the top in troughs. Construction details of the sand. Again, let's here there is a profile of the filter. Number one, you see here that is inlet, water enters, and then at top you have sand, and then here at the bottom you have gravel or support for the sand. So gravel is not media. Gravel is just support for sand. Our media here is single media, that is sand. And you put water from the top and you filter it, and from the right you take as water in number 4 as filtered water outlet. And then you send water to disinfection unit. But after filter clogged, you backwash filter. So number 6, you open the valve number 6, and from the bottom to the top you apply water, you backwash. So it means your flow will be from the bottom to the top, and from the top you will take backwash water from the troughs. Again, here you see here there's another from number as you see here, this is sand, the flow directions from the bottom to the top, and then at the left you see you collect washed, filter washed. At the bottom section AA, as you see here, from the troughs, backwash troughs, you collect the water that you washed out the filter. Again, here there's another picture at the top and left, that is a wash troughs. So you collect water from the top, that is for backwashing, that is for cleaning, that is not during the filtration. So when you filter, you stop filtration, you backwash it. And as you see here, there is a layer that's coal, that is anthracite coal, and the second layer, as you see here, is sand, and then there's another layer that's garnet. And at the bottom, there's a support for these layers that will be coarse gravel. At the right, after filtration, during the filtration, filtered water, you collect it and you send it to clear valve. Again, filter operation. At the left, water from the top to bottom. But when you want to clean it completely, you stop filtration and you apply water from the bottom to the top, and the flow direction will be to up. So it will be from gravel to sand, and from the sand at the top, the dirty water you will collect from the top and from the tube. Again, filter operation. Here I put some pictures to have an idea how it works. One filter during filtration, and when you want to backwash, what happens? At the left, again, that is filtration. At the right, so B is operation during filtration. This is almost 24 hours you do this one, but after 24 hours, it depends again to the quality of water, you stop it. That is operation during cleaning. So you apply from the bottom to the top, and you collect water from backwash water out and backwash tools. Again, some examples of layout and construction details. Again, you see here, this is one filter. At the right, there's a column that most of treatment plants, when you enter, you will see the column. It shows what is the media inside this filter exactly based on the depths that they put here, and you see at the right in the column. Again, here there is another example for multimedia filter. Multimedia filter means the media is more than one media. At the right, if you see here at the top right, At the bottom, that's gravel, that is support, and then there's garnet, sand, anthracite. So anthracite, sand, and garnet, so these three are media, and the support is gravel. At the left, again, you see here gravel, garnet, and redox. These are the layers that you see for this filter. And at the bottom right, you see the real filter. Filters can be on the ground or can be vessels like this, as you see here. Here, as you see here, there's another cut for filter. From the left to the right, you see the layers in this filter. Again, let's see here at the right, at the top, you see one filter here, and the right at the bottom, you see filters. The filters here, as you see, are closed. In the area that are very cold, so we need to cover filters. Why we need to cover filters? In order to not to freeze the water. Again, at the left, you see another filter. This is overview from the top of the filters. Again, at the top left, you see a filter, and at the right, you see the filter that is during backwash. When you backwash it, there's a true at the right and the bottom. When you backwash from the bottom to the top, from the top you collect, that is a true in the center of the filter cell. Let's see here again. There's another picture of it here. That's inlet main at the left top. You put the water and then you filter it. But when you want to wash it at the top, you see wash throughs. You apply water from the bottom to the top and you collect water with wash through. So, but the point is, there's another unit as an engineer you have to design. At the right, you see here, wash water storage tank. Means you need to design what should be the flow rate. If you remember, we did one design in fluid class. We had to size and we had to see what should be the minimum height of this tank. Based on how much pressure you need in this filter, you have to see what should be the height or elevation based on the head, that your total head that you need for the sand filter. And another will be flow rate, what should be in gallons per minute. For example, if you are washing out your filter for half an hour, what should be the flow rate of this tank? And then what should be the height? Based on the height, if you remember, we know what should be the total head. So total head should be static head and dynamic head. So at the center, you see that we have sand and gravel. So during the backwash, you open the valve in E, as you see at the right. So that is wash water storage tank, and from the bottom you apply the water to the top, and from the top you take the dirty water from the top of the filter. Here there's sieve analysis. Sieve in vertical axis, I put sieve analysis, and in horizontal axis, that's cumulative mass percent passing. So here is the one graph I put here for the particles of the filter and based on sieve analysis. But let's see how we can design filters. Based on fluid class, we know that velocity equals to Q over area. In the filters, VA we define as phase velocity in meters per day, or we call it loading rate. As you see at the right, I put here meters cubed per day per meter squared. Most of the textbooks or most of the engineering reports, you'll see the right one. Why this one? Because velocity equals to Q. Q is flow rate onto filter surface, and we know that from fluid class, the unit for flow rate is meters cubed per day. And the surface area of one filter will be meters squared. So Q over area. If I go to velocity, Q is meters cubed per day per meters squared. So Q over area, that will be the unit for velocity. So if you see the velocity will be meters per day. If you cancel off velocity, it will be meters per day. Now there's example. I put here, as part of their proposed new treatment plan, Urbana is going to install rapid sand filters after their sedimentation tanks. The design loading rate to the filter is 200 meters cubed per day per meter squared. As you see here, Q over area. Or if you cancel out, it will be meters per day, or 200 meters per day. That's the velocity of the water in vertical direction. The question is, how much filter surface area should be provided for their design flow rate of 0.5 meters cubed per second? That is the first question. The second question is, how large should the filter be if 4 filters are used? So you need to design what should be the filter surface area, and if you want to design 4 filters, how large should be one filter, how the size of one filter. So solution, we know that the velocity in vertical direction will be Q over area. So area is surface area of the filter. In this problem, Q over area again, if you rearrange, area will be Q over velocity. Exactly the same formula, just you rearrange it. Area as surface will be Q or flow rate over velocity. That equals to, our flow rate is 0.5 meters cubed per second divided by velocity is 200 meters cubed per day per meter squared. As you see at the bottom, we have per day. You have to convert numerator to, we have meters cubed per second, meters cubed per day, in order to cancel off numerator and denominator meters cubed. So 1 day is 24 hours and 1 hour is 3600 seconds. And if you multiply it, it will be 86,400 seconds per day. So please pause your video here and try to find the answer. So the answer will be 216 meters squared. This is the total area for filters. We don't know how many filters up to here in this problem, so that's the total area that you need for filters. In this problem, surface area per filter equals to 216. In problem statement says you need 4 filters. If you need 4 filters, total area that you need for filters divided by 4, that will be 216 over 4, that will be 54 meters squared. That is the area for one filter. However, many states require that the design loading rate be met with one filter out of service. This is every time you need to have one filter out of service. In this case, we would need each filter to be, so surface area per filter will be the same number, 216 per 3. 216 per 3 will be 72 meters squared. So 3 filters will be in service and 1 filter will be out of service. Most of states in the US and other countries, they require to have 1 filter for reserve or out of service. So problem, there is no problem. Determine the minimum number of rapid sand filters necessary to treat a flow rate of 20 million gallons per day if the maximum design hydraulics loading is 5 GPM per feet squared, gallons per minute per feet squared. Assume that maximum dimension is 34 feet and the length over width ratio is 1.2 to 1. Here, this one is FE exam problem. So please pause your video here, try to solve, and then play your video, see what is the solution. Okay, the length based on problem statement, it is 24 feet, and width based on the ratio which is given will be length over 1.2. This one is from problem statement. So 24 over 1.2 will be 20 feet, and area of the filter, surface area of one filter, is length times width. Length is 24 feet and length is 24 and width is 20 feet. It will be 480 feet squared. That is the surface area of the filter. So Q is 20 million gallons per day times 1 day is 24 hours and 1 hour is 60 minutes. And if you multiply it, we will find it will be 13,889 GPM, or gallons per minute. We converted million gallons per day to gallons per minute. Now area will be 13,889 GPM, gallons per minute, per 5 GPM per square feet. You see why we actually converted million gallons per day to GPM, as you see here. So at denominator we have GPM, and also denominator we have GPM. So we want to cancel off GPMs from the denominator and denominator. So if you divide this number to 5, we will find 2778 feet squared. That is the area for filter. But that is the total area for filters. But how many filters we need? Minimum number of the filters we need in this problem. So we need total area of the filters we need is 2778 feet squared, and one filter area we calculate that is 480. So if you divide this number, it will be 5.78. So what should be the answer? A, B, C, or D? Please pause here and see what is the answer. Probably you answered A. But if you go back to previous slides, you will see that, yes, roughly you need 6, and maybe A is right, but that's not. You need every time 1 filter extra as out of service. This is a rule in most of states. You need to have 1 filter out of service. So the answer will be B. You have to be very careful on designing the filters. So the next, as you see here, the single medium filters. This is a picture of single medium filters here. Gravity filters. Why we call it gravity filters? Because you put the water, and water based on gravity enters to the filter media. So it filters from the top to the bottom. Again, see here, there's one picture. At the top, you see wash throughs. These are for cleaning filters. You put water from the bottom to the top, and then you collect dirty water from the top during the backwash. And then you see here a filter sand, that is the media for filter. At the bottom, that is graded gravel. Gravel is not media. Gravel is just for support, that is support for sand. And at the bottom, at the right, as you see, that is perforated laterals, mean you collect water, treated water. Hydraulics of filtration. The first is head loss. When you put the water, so you have to see how much head loss will be in the filters. HL from fluid class we know will be FL over D times velocity squared over 2 times gravity. So HL is frictional head loss, F is dimensionless friction factor, L is conduit length, DC is conduit diameter, V is mean velocity, and G is acceleration due to gravity. Reynolds number, I put here, Reynolds number is 5 times D times VA over nu. If you remember, so try to find Reynolds number in fluid class. So please pause here, go to fluid section in your FE manual, find Reynolds number. If you remember in fluid class, we had Reynolds number equals to d diameter times velocity over nu. But here we have another parameter, that's phi. Phi is shape factor of particles, or will be phi rho d velocity over mu. So you remember these two formulas from the fluid class. At the bottom, I put another formula, that's HL equals to 1.067 over phi times d over g. D is depth, g is gravity, VA is velocity over epsilon squared times sigma CDX over D. And VB will be BS epsilon to 4.5. Epsilon is porosity. Also, please pause here, go to F. Emanuel environmental section and go to filters in water and wastewater section and try to find heat loss. There's heat loss for filters. There's an example here. A rapid sand filter has a sand bed 0.61 meters in depth pertinent data area. So specific gravity of sand is 2.65, shape factor is 0.82, porosity is 0.45, filtration rate is 1.7 liters per second per meters squared, and operating temperature is 10 degrees of Celsius. The sieve analysis of the used sand is shown in the table. Determine the heat loss for a clean filter bed. This is example 10.1. Try to open your book, example 10.1. I'm trying to show this one and then we will solve the problem. So if you see here, at the first column you have sieve analysis, at the second you have weight retained. So if you remember soil class and the soil lab that we had sieves, standard sieves, and we put the soil and we weighted all of the detained or retained solid. Exactly here the same. That is the sand of filter. You take it and you do sieve analysis, and then you measure the weight retained. Again, based on all of the classes, when we talk about weight, we mean mass. It is not right to say weight. All of these numbers are mass of sand. So you can correct it. That is the mass retained. At the column number 3, that is the diameter, that is average diameter of the particles for sieve number 1, as you see here. At number 4, at column number 4, that's Reynolds number. Based on the formula in the previous slide, we have to calculate Reynolds number. Column number 5, that is CD. That is coefficient of drag. And the last column at the right, based on CD times X over D. CD you have from column number 5. X will be percent of retained. So from column 2, divided by D, which is diameter, column number 3. But you have to be careful. Column 2 is 0.87%. When you calculate, you have to divide 0.87, for example, over 100. So after you did all of the numbers in column number 6, so you find the total number, the sum of all of sieve analysis at the right, and then put in the formula as you see here. The next slide is HL is 1.0 at the bottom right, 1.067 over phi times d over gravity times velocity squared over epsilon to 4th times sigma CDX over D. There is problem 10.1 in your book. Try to open your book, pause your video here, open your book, problem 10.1. We want to solve this problem. So here what is given? Again, here is sieve analysis is given. Sieve size from 14 to 20 is given. That's weight retained based on percentage at 0.44. At the right, the diameter based on the feet is given. So Now we want, the problem is asking to find head loss. You need to solve this problem same as this. It will be in your exams. You need to follow instruction on this problem that we try in this problem. First, you have to find velocity. Velocity will be 2.25, q is given 2.25 over 7.48 over 60. So from here, our velocity will be 0.00501 feet per second. So here 7.48 is conversion to feet. So you have velocity here. The second is nu. If you remember fluid class, there is a table in F.E. manual. Also there is a table in your book. Nu, or viscosity of the water, you can find in your book based on the temperature of the water. So here I put here for 10 degrees of Celsius will be 1.4084 times 10 to the negative fifth feet squared per second. That is nu. Reynolds number equals to, again, phi times diameter times velocity over viscosity. So shape factor is given this problem is 0.75. If you remember soil class, so we defined before what is the shape factor. So shape factor 0.75 times diameter, the average diameter. Go back to your notes and the previous slide. You'll see that this is the diameter, the average diameter of the first sieve, and then 0.0051 we calculated in row 1, as you see here, that's a feet per second divided by nu. If you calculate, it will be 0.876. That is the number. And what is the unit for this one? That is unitless, no unit for Reynolds number. CD will be 24 over Reynolds number. 24 over Reynolds number. Why? Drag coefficient. Why we use? If you remember previous session, or if you remember FE class, go to environmental section and see what is the drag coefficient. We have three formulas. The first one is 24 over Reynolds number. That is for laminar flow. Why? If your Reynolds number is less than 1, we classify our fluid as laminar flow. So CD will be 24 over Reynolds number. So from here, 24 over Reynolds number, you calculated 0.876. That will be 27.4. Now we calculate CD. We have to calculate the last parameter that we need for our tables. CD times x over d. CD we calculated here, that is 27.4 times x is percentage of retained on each sieve. So 0.44 is given in the table, but you have to divide 0.44 over 100. Why? Because that is per percent. Per, as you see, 0.003283. That is the average diameter which is given in the tables. So if you calculate this one, will be 36.7. So we calculated here three parameters. First is Reynolds number, 0.876. The next is CD, that is 27.4. The last is CDX over D, that is 36.7. Now let's go back to the tables. Again, at the first column we have sieve size, then weight retained in percent, that's 0.44. The average diameter of the particles for sieve number 1. Reynolds number, we calculated in the previous slide, we plug it in here. Then CD, again, we calculated, we put in here, and the CDX over D, we calculate when we plug it in here. Now for the second sieve, exactly same as this one, go and find Reynolds number. Please pause your video here and go back to previous slide and see how we calculated. But the difference here, as you see here, for Reynolds number is the diameter. Everything is same except diameter. So Reynolds number is 5 times diameter times velocity over nu. So everything is same, just you change diameter. If you change diameter, the first number for the second step will be Reynolds number, will be 0.622. Again, you see that this number is less than 1. Our flow is laminar flow. You will use 24 over Reynolds number. So 24 over 0.622, that will be 38.56. The last column is CD times x over d. CD you calculated 38.56 times x here from the second column, that's 14.33, but that is that's percent. It means 14.33 over 100. Again, over the last column is D, which stands for the average diameter, and average diameter here is given, that's 0.002333. That's in feet. If you calculate, it will be 2368.4. So again, pause your video here. I need you to pause your video and calculate any of these, and after play your video. So the Reynolds number, the next number for the CF number 3, again Reynolds number, same formula, just you change diameter to 0.001779, and if you calculate, it will be 0.475. And again, you see Reynolds number is less than 1. The CD will be 24 over Reynolds number, and it will be 15.57. And same as previous one, CD times x over d. CD, you find it here, 50.57 times x from second column is 43.22 over 100 over, and d again is here given. Diameter from third, it will be 12 to 84.9. Same as this one. I need for any of these numbers, pause your video, try to practice and try to find these numbers and then play your video. For the next one, Reynolds number, again, same formula, just you change your diameter to 0.001500 from the fourth row. If you change, so Reynolds number is 5, it is 0.75 times diameter is given, velocity you calculated over nu. So the number will be 0.4. Again, this number is less than 1. CD, the formula will be laminar flow, and the formula for laminar flow is 24 over Reynolds number. 24 over 0.4 will be 59.97. Again, CD times x over d, again you calculate here, CD is 59.97, x is 24.07 over 100 divided by diameter is 0.0015. If you calculate, it will be this number, 10822.9. So for any of these numbers, I need you to pause your video. The next number, Reynolds number, is 0.336. Will be 71.51 because that is laminar flow, and CDX over D will be 55.47.9. Again, Reynolds number for the next CF, just you change diameter, it will be 0.282. Still, that is less than 1. The number will be 85.03, and then 3391.4 CDX over D. You calculate the next number will be 0.237. Will be 101.3, the CDX over D will be 6116. And then again, the Reynolds number 0.199, still that is less than 1. Laminar flow 24 over number will be 120.59. Last number will be 468.8. And then the Reynolds number you find 1.555. That is, as you see here, now that's changed. So if it is larger than 1, you find your CD, and then you calculate, that will be the number 361.8. But check this number. So check this number. If Reynolds number is larger than 1, you need to change your formula for CD. If this number is less than 1, check, maybe there's a typo here. Intentionally I put here for you to find this number. So check the last row, see that Reynolds number is this number or not. If that's less than 1, you have to change the last row. Intentionally, I put these numbers. Check the last row. So after you put the last column, you have to sum all of the numbers. Sum from 36.7 to 361.8. So if you sum the column, the last column, the number will be 35,898.8. So this is the what we get from this table. So how we can find head loss? The head loss will be 1.067 over 5 times d over g VA squared over epsilon 4 sigma CDX over d. So phi here, so HL will be 1.067. Phi is shape factor, that's given. That's 0.75. D is depth of filter, that's 2.5 feet. G is gravity, because we work in a US system, that will be 32.17 times velocity will be 0.00501 squared over epsilon, that's given. Porosity of what? Porosity of the particles of the filter, that is 0.41 to 4 times sigma CDX over D. You calculated from the previous table, that's 35,898.8. So pause your video here and see what is the answer. So if you calculate, the answer will be 3.53 feet. So the head loss for this filter is 3.53 feet of the water. So we done filtration here.